Hello again everyone, welcome back to ptet.chemistry channel. This is the start of this section B on topic 5 in my classification. That is on chemical energetics to do with enthalpy changes, all those formation, combustion, bond energy, calorimetry, that kind of thing. In this section B type of questions, where 1, 2 and 3 are correct, there will be option A. 1 and 2 are correct is option B. 2 and 3 are correct is option C. Only 1 is correct is option D. This is quite common in the Cambridge International A-Level paper 1, obviously. But if you are from another specification, the content that are being covered by these questions are actually very good because they assess you on multiple concepts and your logical reasoning in terms of using what you have learned in A-Level chemistry. So they'll be useful to you regardless. In this first question, is basically about the conversion of graphite to diamond. So we're trying to think about turning the graphite from the pencil itself going into diamond. The enthalpy change being plus 3 kilojoule per mole. That's what they're saying. Okay, so it seems like a really small enthalpy change. So that means they only need to absorb a little amount of energy from the surrounding to go from graphite to diamond. But in reality, we know that diamond takes ages and ages to form from your pencil graphite itself, right? Okay, so if we go straight to number 2 first, so the bond energy of the carbon-carbon bond in graphite is greater than that in diamond. They're asking for correct statement. Which of the following are correct statement? If you think about graphite, so graphite is like that. Each of the carbon, so they are continuous network, okay? Each of the carbon is a 3 bond pair and 0 lone pair. So there is a carbon sp2 hybridization. In a diamond, however, you have each carbon bonded to 4 other carbon. Okay, so that carbon will be, each carbon will be 4 bond pair and 0 lone pair. And you know there's tetrahedral, there's carbon sp3 hybridization. You can refer back to the structure and bonding tutorial playlist where I talk more on hybridization and how to work them out. Okay, how would you be able to decide which carbon-carbon bond is actually stronger? So there is carbon sp2 versus carbon sp3, single bond versus single bond. But this one has around, you can think about it, it has around 33% S character. This one has only about 25% S character on each carbon. And when you think about S orbital, okay, so the S orbitals are spherical, and they are the one that they give you the greater contribution of the stronger sigma bond. So we can think about this as a result of having greater amount of S character refers to the orbital character. Okay, so this bond is stronger CC in graphite versus the CC single bond in diamond. So number 2 is actually a correct statement just by thinking about the hybridization and the covalent bond that they form between the hybridized carbon. Okay, if I go straight next to option 1, talking about the atomization of diamond versus the atomization of graphite. Okay, so if I talk about atomization, so maybe I can use the space here. All right, okay, so carbon into gaseous atom, because definition of the enthalpy atomization is forming 1 mole of the gaseous atom from its element or from its substance. Okay, but the idea is forming 1 mole of the gaseous atom. So that forms that. You can interpret that as enthalpy of atomization of diamond, and you can interpret that as enthalpy of atomization of graphite. And we know the enthalpy change of this reaction, so we can think about relating enthalpy of atomization. So that is delta H for the reaction, which is plus 3. Okay, so if we look at option 1, I'm just thinking about space. Okay, I'll go here. Okay, so in terms of Hess law, if you apply Hess law correctly, going this way is the same as going this way and then going that way, so you have to minus that. Okay, so delta H is equal to delta H ATM graphite minus the delta H atomization of diamond. Okay, so it's saying that enthalpy change of atomization of diamond smaller than graphite. So if diamond is smaller than graphite, as in the atomization, that means the delta H will be positive. If that is true, if the atomization of diamond is smaller than the atomization of graphite, then bigger value minus smaller value will give you positive, and you get positive, and that is true. Okay, so number 1 is correct. Okay, number 3 is talking about combustion of diamond greater than the combustion of graphite. So we're gonna do similar kind of hash cycle, but running out of space here, so I'll write somewhere else. Maybe I can write there. We go from graphite to diamond. Option 3 is about combustion. So this is burning in oxygen, okay, plus oxygen, okay. We'll give you CO2. So this is the combustion of graphite. Maybe combustion, I just write delta HC, which is what most books will have done. Combustion of diamond. And that is your enthalpy change, which was plus 3 as well, because this enthalpy change reaction is something that was given already, but we can relate it to atomization. We can also relate it to combustion depending on the reaction. Here is combustion, that's why you get CO2, complete combustion, because that is the definition of enthalpy of combustion. Okay, so the delta H equal to the combustion of graphite minus the combustion of diamond. If you follow the hash cycle properly, you go this way and then you have to go that way in order to reach back there. So you have to do minus that. So it's saying that enthalpy of combustion of diamond greater than graphite. If diamond has a bigger value than the graphite combustion, so this minus this will give you negative, but you have a positive value. Okay, so option 3 must be incorrect based on your expression as well as based on information given. So it has to be this bigger value than this, only then you can get positive. Okay, so therefore only 1 and 2 is correct, so that is option B. That is correct option. Next question. So this is again application of Hess law. So they love to ask you to apply Hess law, but sometimes they do ask you to define what is meant by Hess law. So the enthalpy change of a reaction is independent. So this going from R to S, the enthalpy change of this reaction does not depend on what route you take. You can go from here to here to here, as long as you start from the same point and end at the same point. Okay, so going from T to S, I can go this way and then this way, but I don't have a value here. Or I can go this way and then this way. Okay, so what I'm going to do is I'm going to go this way. So the enthalpy change would be minus 75 because you're going in the same direction. Go in the opposite direction, so you have to do minus plus 92. Without putting into my calculator, I can see that minus and then minus again. So that delta H is going to be lesser than 0, and endothermic is wrong. It will be exothermic, which is enthalpy change lesser than 0. Of course, you can put into calculator, and there's something that they might ask you to do in the theory paper. It's just that I hope you can see that minus this minus that is going to give you a negative value. Okay, so 2 is wrong, only 1 is correct, which of course you can check really. If you want, you go from U to R. For the same reason, you don't go here, you can go here, but you don't know this value. So you can go this way and then this way. So the delta H, you can go plus 92 and then minus 134. Why is that one incorrect? Huh? Let me think. Why is that one? That is weird. Does it give you plus 42? I know. Okay, so I'm not only going opposite this, but I'm also going opposite that. So I've done a mistake here, quite careless mistake. Yeah, it shouldn't be plus 92 because plus 92 is going this way. So this one should have been minus 92, and then that makes sense because I got 1 is the only option that's correct. By working out 2 is wrong, right? So minus 92 plus 134, then you can get plus 42 kilojoule per mole. So that is indeed correct. Okay, Ooh, scared me for a bit there. And then R to T, if I change to a different color. So R to T, if you want to work out this thing, you can go this way, and then this way, and then this way. But of course, we know 2 is wrong, 1 is correct. We don't have to work it out. I will work it out anyway, because I'm not in a hurry for time. So if I want to go this way, I will go this way. So I'm in the same direction. So there's minus 1, 3, 4. I'm in the same direction. So there's plus 92. I'm going in the same direction, right? Okay. And then I need to go opposite direction. So I have to do minus and then bracket minus 75. If you put that into a calculator, minus 134 plus 92, minus become a plus. And then your calculator don't show you the plus. But you know, as you're dealing with enthalpy change, you always have to have a sign, a value, and a unit. So it's not a minus, it's actually a plus 33 kJ per mole. Okay, obviously you don't have to work them out once you know 2 is wrong, but you never know in a theory paper that you need these skills as well. Okay, so moving on to the next question. It's kind of similar to the previous question. So the enthalpy change is different now. It's no longer plus 3 given in the earlier question. Regardless, it is still endothermic. Okay, it is still endothermic because the enthalpy change is greater than 0. So this is about producing synthetic diamond. Which statements help to explain this? You have an equilibrium existing within diamond and graphite. That is totally rubbish because this is not an equilibrium. Not an equilibrium. Okay, it doesn't exist like half that. No, it's not an equilibrium. Okay, 2 is wrong. You only have one option. Okay, and you obviously know that just because the enthalpy change is very small does not tell you how fast the reaction is going, because this is to do with rate versus thermodynamics. Activation energy affects rate of reaction, whereas when you have enthalpy change in A2 in A-level chemistry, you will learn more on entropy, and you will learn more on Gibbs energy change, and they will tell you more about thermodynamics, yeah, whether it's spontaneous or not. Okay, and then only exothermic reaction can be made to occur readily. Not necessarily, because as I mentioned just now, it's to do with entropy and also Gibbs energy change. Okay, this one is more of an A2 concept in the Cambridge International syllabus, but it might be covered in the other UK A-level curriculum much earlier. But it's all down to delta G, whether it's spontaneous, whether it occurs readily or not. It's not just looking at enthalpy, we also have to look at entropy and the temperature at which the reaction happens to determine whether it's spontaneous or not. Okay. This question 4, it's saying that which of the following enthalpy changes can only be obtained by applying Hess law. So we have to think about what we know. Let's talk about option 2 first. So if you have formation of methane from its element, so carbon plus hydrogen, you need 2 hydrogen. I'm writing the stat symbol because enthalpy of formation is all about forming 1 mole of the substance from its elements, all in their standard states under standard conditions. So can we do this? Can we work this out straight away? Well, I mean, that's the enthalpy change of formation, you see. So the enthalpy change of formation of this is 0. The enthalpy change of formation of this is 0. And you want to find this, which is actually the enthalpy of formation of CH4. So you can't really do it directly. But what you can do is you can do via combustion. Okay. So the combustion, this will be via the enthalpy of combustion. Okay. Where you do the sum of the enthalpy of combustion of reactant minus the sum of the combustion of the combustion enthalpy of the product. Okay, so number 2, you cannot obtain directly. You can only obtain via application of Hess law via the enthalpy of combustion. Okay, how about option 1? So when we look at option 1, what are we doing? Anhydrous mean no water of crystallization. So we started from CuSO4, and then you add 5H2O, and then you get CuSO4 with 5 water of crystallization. hydration. So what can we be thinking about? I guess you can be thinking about is dissolving that in water. You can get SO4 2 minus aqueous plus 5H2O. So the reaction here is dissolve in water. You will have MC delta T, which is delta H1, delta H2, MC delta T to M2, because you're measuring the enthalpy change for reaction 1 and reaction 2. And then you can work this out. You can work this out via the Hess cycle, and this is quite popular in practical setting. They can ask you to do this, they can ask you to do that, and then use the Hess law to work out enthalpy change. So can very easily a full practical paper question as well, yeah. But there's no way you can work this out directly, so you have to use Hess law there. Okay. How about combustion of glucose? Okay, so combustion of glucose, we can be thinking about. Let me think. So going back to the previous question, I mentioned that we are using calorimetry, but just by using calorimetry on its own, you can work that out. By using calorimetry on its own, you can work that out. But this thing on its own, by dissolving copper sulfate into H2O, you cannot just work out by calorimetry on its own. Okay, it wouldn't work that way. Okay, and that's because they do not form the 5H2O straight away, because when you think about it, when you dissolve in water, you're going to dissociate them into copper 2 plus and SO4 2 minus, your water around you. This only forms when you start to crystallize them out, and there's no way for you to determine that directly. Okay, even though you do calorimetry on the side, but you still have to use Hess cycle to relate them together. Okay, whereas the next part, which is the combustion of glucose, in fact, a lot of organic compounds, you can get their enthalpy change of combustion by doing calorimetry. Okay, calorimetry alone will be enough. Okay, can do calorimetry. Okay, this can happen in a paper 3 or even a paper 5 setting, where you have combustion or something. I can't draw very well, but you can have the combustion of the glucose, and then you burn it. Okay, is that how it goes? Yeah, and then the heat get transferred to the water above. Okay, you have thermometer there, so you combust the glucose, and then it will heat up the water, which is the surrounding, assuming that all the temperature from the combustion goes into the heating of the water, which in reality doesn't happen. That's why it's not 100% foolproof kind of experiment. That's why you can think about heat loss kind of thing as your error. Okay, so what happened is you can have C6H12O6 combusting in O2 to give you CO2 plus H2O, and that's not so bad, because there's 6 CO2, there's 6 H2O, there's 12 plus 6, there's 18 minus 6, there's 12, so 6 O2. So you can work out the mass, okay, M1, and then of course you need the mass of the water. So you have the water, which is M2, you have the heat capacity of the water, which is the C, you have the delta T, which is the TF minus TI, and then to work out the enthalpy change of reaction, you just have the MC delta T, which is of the water, divided by the mass of the glucose over the MR of the glucose, assuming all the heat from this get transferred into here. Okay, and you have to do a minus, because this is the system that give out the energy, this is the surrounding. So the temperature delta T, TF will be higher than TI. Delta T is positive, but the reaction which is from the system is negative because it gives out the energy. Okay, so you can get combustion of glucose in any organic compound by doing calorimetry experiment. You should probably write that out better, but you should be able to spell that, and you know the idea about calorimetry, because that can be asked in a practical setting as well, yeah, under planning section. This is the last question of this 5-question series on section B type of question. There's on enthalpy change. So if you want to calculate the enthalpy change of formation of gaseous sodium ion, so state symbol are very important. What do you need? Okay, we can construct some very simple cycle. So from the sodium solid, we can get sodium atom. From the sodium atom, we can do first ionization energy. So this is what you want. What do you need? You need the atomization of sodium. You need to multiply that by 1 because you're just forming 1 mole of gaseous atom. And then you have the first ionization energy of sodium because you're going from 1 mole of gaseous atom, losing 1 mole of electrons, okay, to form 1 mole of gaseous ion with a single positive charge. These are the kind of theory level questions they like to ask you to define whether you're in paper 2 or sometimes they can ask you in paper 4 as well, okay, because anything from NS can and will be asked in A2. And that's multiplied by 1 as well because you're just forming 1 mole of gaseous ion with single positive charge. You need the first ionization energy of sodium. You need the atomization of sodium. You do not need the enthalpy change of formation of sodium because the enthalpy change of formation of sodium is equal to 0. Sodium forming from its element sodium, that is sodium solid forming sodium solid. There's no enthalpy change involved at all. Okay, so only 1 and 2 are correct. The correct answer will be B. Okay, that's the end of this video. If you have enjoyed these video tutorials on my channel, please do subscribe to the channel and share the words to your friends, your group chats with your classmate, and your seniors from school if they are in upper 6, your junior from school if you are in lower 6, and whoever else you think the videos on my channel might benefit. Okay, thank you for watching.